All right, help me out. F prime of x was 2x plus 2. Did you all realize you had to go up to f of x, which is plus 2x plus a constant? Do we have enough information to solve for that constant? Yes. When x is 0, y is 1. So 0, 0, c. C equals 1. So f of x is x squared plus 2x plus 1. Yes? Does that look familiar? Let's take out our worksheets. All right, we did the first problem together. We got 4 for A, 8 and 12 for B, 4x minus 4 for C, and 4 times x minus 1, which is 4x minus 4 for D. Yes? What was A of 2? Oh, I had it there. 4, 6, and 0. All right. I'm ready to make a connection. Where'd that 4x minus 4 come from? Because we just used geometry, right? I mean, it was a constant function. It was y equals 4, f equals 4. Constant function. Rectangle. 4x minus 4. What was that rectangle? Area. It was the wasn't it the antiderivative of 4? Is it 4x the plus c? An antiderivative of 4? Yes? Okay, keep that in mind. Part 2. All right, let's do this part together. You're to finish this for homework. Do we all finish it? I guess I should take a step back. Did you finish it and just finish it? Or did you finish it and understand what it was really getting you, trying to get you to put together? Did you understand what it was trying to get you to put together? Some of you saying no. Some of you say, yeah, I get it. I'm good. I know what it's trying to get me to do. I see the relationship. I'll be like, I could use some more explanation. All right, here we go. So right now, listen, just big idea. Right now, we're taking geometry concepts, finding area functions, and making observations. Oh, look, that area function is related to the original function this way. All right, so let's do that. Part A, Part B, awesome. Part C. Okay, Part C. As a guide, compute the integral. This is read as the integral from 0 to x of f of bless you, d bless you. All right? You're welcome. So that is saying find the area under the f function from 0. Area, stop at x. I don't know where x is. And we're going to learn later today, x could actually be before 0. X could be anything it wants to be. It's a variable, just like all of you. It could be anything you want to be. But for the most part. If not, I'll talk to you later. All right? Boom, rested. All right. What is the base? It's not a triangle. Let's not call it a base. How many of you did a trapezoid here? Okay, if you did a trapezoid, this is actually the height of the trapezoid. The bases would be 2 and, well, this base depends on x. Do you agree? It depends on where x is. Well, Specifically, it's 2x plus 2. Do you agree that is a y value? And y is 2x. It's actually 2t plus 2, but at x, it's 2x plus 2. Does that make any sense at all? Okay. So I have 1/2 area of a trapezoid is 1/2. The bases added together, 2 plus 2x plus 2 times the height, which is x. Now, you're supposed to clean that up and put it in polynomial form. Did you get x squared plus 2x? X squared plus 2x, yes? Okay. X squared plus 2x. Did you notice? Remember using this notation? The warm-up problem, what did I call it? I called it f prime. We had to go up a layer. It was called f. But what if you're calling this f? Is it up a layer, capital F? Remember that? All right. What is the antiderivative of 2t? T squared. Very good. Plus 2t plus c. That is the antiderivative of f of t. Let's see if you really piece this together. The majority of you said yes, so I'm going to go ahead and challenge you. Why is that antiderivative a function of t and the area a function of x? It's the same function, like the same value, but one's a function of t, one's a function of x. Why? Okay.
Is it because the range on the integral is from 0 to x, not 0 to t?
Very good. Very good. Question for you, because I am an off-topic teacher. Do you know enough to tell me what that means? If v of t is velocity. Velocity is a function of time. Do you know enough to tell me what that means? Cool.
The distance traveled over the interval AB.
Close. Close. Very close. This is v of t. Okay. This is not to scale. I just want to make some different numbers here. Doesn't this say to find, I'm going to call this, we're going to go generic, then we're going to make it specific, okay? We're going to call it A to B. We're going to go generic, then make it specific. What does this tell me to do? Find the area under V of t between A and B, okay? Let's do it. This is a triangle from 0 to 6. Okay? Base is 6, height is 4. What's the area? 12. All right, this is a triangle. Base is 4, height is -8. What's the area? 16, but it's below the x-axis, below the t-axis. We're going to call it -16. All right, are you with me? When did the particle change direction? At 6. The velocity was positive, then 0, then negative. From 0 to 6, the particle moved to the right. How far? 12 units. Because the area under a velocity curve is how far it went to the right, because it's a positive velocity, right? Then what? The particle moved to the left. Still? Left. How far did it move to the left? It moved 16 units to the left. Okay. What is the integral from 0 to 10 of v of t dt? -4. Very good. What does that mean? Displacement. Okay, so we need to be careful. Cole is on the right track. He said distance traveled. Now listen, you guys love to see me walk. I couldn't go a day without you guys getting to see that, okay? Because I give the audience what they want. All right. So I am here. I don't know where I am. I'm confused. Old man. All right. What if someday I am and I'm still teaching calculus? It'd be so sad. Which way was I walking again? And I'll be really confused because for however many years, 35 years, I do everything in reverse for you. Because when I'm walking to your right, I'm actually going to my left. I'll say to the right. And I'll be confused. All right. I'm having some introspective sadness right now. Okay. It's terrible. Let me finish this. All right. Where was I? All right. I am here, not knowing where I am. We'll get to that in a minute. I moved to the right because my velocity is positive. How many units did I move to the right? 12. But then I moved 16 units left. I am further to the left than where I started. How many units further to the left? 4 units to the left of where I started. That's a question of displacement. Does it mean that I'm at a position of -4 on the number line? This is so important. It does not mean I'm in a position of -4 on the number line. Because what if I started over at 30? If I started at 30, here we go. If I started at 30, where did I end up? 26. I went from 30 to 42, and then 42 minus 16, I ended up 4 units to the left of where I started. But what if I started at 10? It doesn't matter. Wherever I started, that area is going to tell me my displacement from where I started. 4 units before where I started is the meaning of that. Okay, flashback another. I'm trying to build this up for you, okay? Do you remember the, was it liters of oil? Help me out. There were 50 liters of oil in the tank when the time started. And then there was that table. And we did, I forget if it was like maybe a right Riemann sum. And we found out the area. Remember the area? And it said how many liters of oil are in the tank at the end. Didn't we have to include the 50? 50 plus the displacement. Same thing. But not a number line. A level. Started at 50. Might have filled up. Might have drained. Isn't the area the displacement of oil? What would that mean? The net change of the volume of oil. Does that make sense? They're going to test this so much on the AP test. This is called the integral as an accumulator function. The integral as an accumulator. What's an accumulator? Well, an accumulator of miles per hour is miles. An accumulator of liters per minute is liters. They're going to test you on that. Okay? Here's a free response problem. There were 30,000 mosquitoes on an island at day 10. No, I think it was day 0. It doesn't matter. 30,000 mosquitoes on an island at day 0. Okay? Because you're just think about it. The rate of change of mosquitoes in mosquitoes per day is given by this function. How many mosquitoes are on the island after 20 days? Do you see how you have to do an integral over the 20 days and then add on the 30,000? That's what they're going to test you on. You have to consider that. So we'll go back to Cole's question. Ready? I start here. I walk to the right 12. I walk to the left 16. What is my total distance traveled? 28. My legs, they don't feel like I walked 4 units. They feel the 12. They feel the 16. They feel the burn. No. They feel as if both of those were positive. Because even though I walked to the left, it felt like I walked 16 units. The total distance traveled would be this is not for today, the absolute value of the velocity, then added up. Treat this as positive 16 and then add them up. We'll save that for another day. Does that make sense though? Displacement, net change, total distance traveled, total amount of feet traveled. Okay? We get it. Okay, that's the meaning. There's a picture that we're familiar with. Back to the story. Okay? Actually, more to the story. I get on these topics and I'm like, oh, this is going to build right into that. And then I get sidetracked, as if you didn't know. Can you guys tell me, especially physics people, you're going to make connections today that hopefully you've been considering for a while, but maybe never connected. What's another way to write displacement? You define displacement. You never define displacement as the area under the velocity curve, like the integral of velocity from A to B. That's just not how you did it in physics. What's displacement?
Change of position.
Good. Be more specific. Let's math it up a little bit. What do we call our position function in this class? We called it S of t a lot. Remember that? I mean, it annoyed us because that's what we thought speed. No, position, right? How would I write displacement from 0 to 10? Done. Change in x would be 10. Change in position. How do I write that? Notationally. S of 10 minus S of 0. Right? Final position minus initial position. Oh, that's how far I was displaced. Final position minus initial position. Displacement. Does that make sense? Wait a minute. Let's generalize this. The integral from A to B of v of t dt is, this is a B, S of B minus S of A. Whether you realize it or not, we just showed the fundamental theorem of calculus. Okay, it's going to be called the fundamental theorem of calculus. That is an incredible statement right there. Let's pause and think about what that means. I really need you guys to focus. Okay, this is not going away. Ready? Crazy velocity function. Crazy velocity function. No longer any nice, easy line segments that are going to make triangles. Okay, crazy velocity function. Even that last problem, that is it d prime of x? Is that what they called it? That one. Crazy velocity function. Ready? A, B, area. Isn't that blue area the integral from a to b of v of t dt. Yes? How do I calculate that? Should I use some left Riemann sums? No. Should I use some right Riemann sums? No. Midpoint? No. How do I find the area under a velocity curve from A to B? S of B minus S of A. Wait a minute. So if I can find the antiderivative of this thing, which I can if it's continuous, remember, to be integrable, the function just had to be continuous. Wait a minute. If I can find the antiderivative of velocity, then all I have to do is plug in B, plug in A, and subtract. That's how you find the exact area under a curve. Antiderivative, plug in the final value, x value, minus, and then plug in the initial x value. Come on, isn't that crazy? To find the area under a curve, you take the antiderivative, plug in the final value, plug in the initial value, and subtract. Not so hard. Okay? Let's test it. We've done this before. Ready? 2x's. It's going to be triangular, or in this case, it's going to be a trapezoid. But let's not do it geometrically anymore. We're not going to do base and height and trapezoids and all. Let's see if this is really true. Now, I gave you this V of t application because I think it makes sense to you. Area under velocity, okay, displacement. But that's not always the application. What if it's just some random function? Ready? What's the antiderivative of this thing? X squared plus c. So if this is little f, then capital F is x squared plus c. And what did we decide we're going to do? Take the antiderivative, plug in this problem, 4, plug in 1, and subtract. Well, what's capital F of 4? 16 plus c. What's capital F of 1? 1 plus c. 16 plus c minus 1 minus c. What's the area? Using geometry? Using a trapezoid? No, using an antiderivative. That's the calculus behind it. Okay. Well, that's not a curve. You said this was for curves. All right. Let's make them easy. Let's go. Let's go 3x squared dx. Keeping it easy. Okay. You told me to do what again? Take the. Now I don't know what this is called. I don't know if it's called little f. It doesn't matter. If that's little f, what's capital F? X to the third plus c. Plug in 5, plug in 2, subtracts capital F of 5 minus capital F of 2. What's capital F of 5? 125 plus c. Minus, what's capital F of 2? 8 plus c. 125 plus c minus 8 minus c. Oh, look, the c's are going to go away. Talk about that later. What's 125 minus 8? What does 117 mean? The area under 3x squared from 2 to 5. Using rectangles? No. And you couldn't use trapezoids because it's curved. Using antiderivatives. Come on. That's pretty cool. Right? The person who discovered that, I mean, it's just amazing. Oh, look, the exact area under a curve comes from an antiderivative. Now, for those of you who this drives you nuts because we didn't take any formal notes on this. Okay? Just so you can plan ahead. This is the approach we're taking. Concept today. Big idea today. Discovery today. Go over the worksheet. We're going to formally write all of this out in 5-4. We're going to formally write all the fundamental theorem of calculus out, all of it in 5-4. You understand that? So don't stress out about, oh, I didn't get that down. Like, it's okay. All right, let's verify. I think I went from 2 to 5, didn't I? From 2 to 5, and it was 3x squared? $117. All right. So there's the part you're finding. I can't even, I can scroll up to it. But there you go. So what does this mean again? If your velocity, and I don't know why you would be able to tell that your velocity is defined by 3x squared. But if your velocity is defined by 3x squared, and you go from 2 to 5 minutes, then you've gone 117 meters in a minute, like meters in those 3 minutes. Like, does that make sense? Like, this is your meters per minute. You have go this many minutes. That would be the meaning of it. 117 meters. Are we getting it? Big idea. So back to the story. Back to this problem. Why is, if we started with t's, this is what I was trying to get at. I think this will make more sense to you now. If this started with t's and this had an x in it, Caden answered for us, why does area have x's in it? And Caden said, well, x was where we stopped, and that area depends on x. It depends on where you stop, right? It's a function of x. Area becomes a function of x. Did you all get x squared plus 2x for that one? But what if we go from not 0 to x, but -1 to x? What does that affect? Does it affect the x squared and the 2x? Hang with me here. Does it affect the x squared and the 2x? For part E, x squared plus 2x. No. Where did that 1 come from? Geometrically? What's that? Good. Yes. Remember the plus c? Doesn't the plus c depend on what point you're given in the original function? Doesn't the plus c, wasn't it the difference between starting from 0 to x and then -1 to x? Isn't it that plus c? It's a constant area we started with. It's a 1 that we started with plus the displacement. It's a difference between starting at 0, okay, and starting at 1. How far did I move? X squared plus 2x. Plus 0, plus 1. How far did you move? X squared plus 2x. Plus where you started. Does that make sense? All right. All right. So what about this table? Check your work. All of these should be functions of x's. They should not have any t's in them. If you have t's, it's not right. Sorry. Why? Because area depends on x. And that was just because of this application problem. If I said find the antiderivative of f of t, it's going to have t's in it. But once you jumped into area, wasn't the base of those objects or height of the trapezoid, weren't they functions of x? So the areas became functions of x based on the context of the problem. So then what are the derivatives? Have to be functions of x. What did you notice? What did you notice between columns 3 and 1? They're the same. Which means column 2 must be the antiderivative. Because what happens when you take a derivative of an antiderivative? You're back to where you started. You're back to column 1. Which means column 2 must have been the antiderivative. Column 1. So what do we realize? The antiderivative function is what generates those areas, which is what I showed you through the velocity and position example. Are you with me? I get hesitant to discuss it this way because it's very conceptual first before being concrete. And my philosophy is always typically to start with the concrete and then work to the abstracts. But this is one of those scenarios where they're going to test your understanding of this so much. I wanted you to say, oh yeah, that is calculating displacement. It must come from the antiderivative function. Was it too much or are you guys okay? All right. So then, if you really understood all this, then hopefully you didn't stress out too much about what goes in this box. All right, let's break it down. This is the part that usually trips people up. Let's call this, well, I don't call it. They told me it's called little f of t. You're looking at the little f of t graph. But did anyone try to find the antiderivative of that thing? Because technically, if we go back up to what we just did, column 1, column 2, column 3. Here we go. Ready? Column 1 would be f of t. And I would put the 0.2t sine of cosine of sine of t. Yes? Column 2. They called it d of x. What would d of x be, just in general? The antiderivative of that. I don't know what that is. And you're not going to either. Okay? I don't know what that is. But that's not what they asked us for. They asked us for d prime of x. That's column 3. So we're actually back to column 1 with, not t's, x's. So in this answer blank, you should have had 0.2x times the sine of cosine of sine of x. Does that make sense? Why now? Okay. All right. One last thing. And I'm kind of teaching 5-4 already. So here, I need to be careful here. Make believe this is a velocity function. F of t is a velocity. Velocity, what is the shaded area? What would it mean? So meters per second would be the curve. Area, meters. Displacement, right? Displacement. How would I find it by hand if I could? What would we decide? Take the antiderivative. What would it be called? Capital F. Plug in x, plug in, and subtract. So do you agree, if I wanted to actually calculate d of x by hand, I would do capital F of x minus capital F of 0. Do you agree with this? Symbolically. I don't know what the capital F function is. Pretend that we know it. I would plug in x, I would plug in 0, I would subtract. Yes? What is the d prime function? I know the answer. That's not what I'm asking. Symbolically, are you ready? What's the derivative of capital F of x? Little, bless you. What's the derivative of capital F of 0? Careful. What's the derivative of capital F of 0? 0. Ready? Antiderivative, capital F. Plug in 0. What are you going to get out? A number. What's the derivative of a constant? 0. So capital D prime. Capital D prime. Do we need to take a moment? Okay, my sons have been playing with my niece's phones. So there we go. Oh, there's a Christmas picture. They're so weird. Where was I? All right. This tells you the answer. Capital D prime is F of x. What's F? What's x? Oh, F of x. It's little f of x. Okay. So we just proved that that will work for every case. That's a lot to take. All right, that worksheet, I always think it's worthwhile. It gets you thinking about geometric connections to the fundamental thing of calculus. All right, do not lose that. We're going to refer back to that multiple times, or at least in your mind, you can refer back to it. All right, so let's get into 5.3 a little bit. So you're going to have some homework. That's right. Get excited. Huh? Ask Wendy. I don't know. Ask Wendy. Wendy makes the decisions for the whole district. Huh? Wendy. Don't you hate that? Tell people put tons of pressure on you. For no reason. All right. So, we're not going to do this right now. This is going to be part of your homework because I don't want to spend class time on it. So, leave room to write down these properties of integrals, these rules for definite integrals. They can be found on page 285. Page 285. You're going to write down these properties. There are 7 of them, the last one being the Mr. Westphal property of ping pong. Domination. All right, so a quick rundown. This, we're not like well trained enough to recognize this, but this should start to look off to you. What's wrong with this integral? Huh? Yeah, what's wrong? We've always written it a to b, and now it's b to a. Okay, here's a property. The integral from a to b is the opposite of the integral from b to a. What does that mean? That means if I start adding up areas from left to right like I should, if I add up areas from right to left, it's going to be the opposite value. So if I go backwards in integration, I need to account for, or the math will need to account for it being the opposite value. So if my integral from left to right was 4, then if I go right to left, it'll be -4. Does that make sense? Okay. We'll practice that later. All right, those are the kind of properties these talk about. What kind of area are you going to get if you go from 5 to 5? 0. You haven't accumulated any area. All right, 0. And those are the properties we're going to practice. Now, let's practice some of them. And you're like, well, I haven't written them down. It's okay. These are pretty logical. Suppose the integral from -1 to 1 is 5. 1 to 4 is -2, and -1 to 1. Oh, look, this one is under F. This one's under H. We need to be careful. They're asking me about F. So the integral from 4 to 1, ooh, that looks wrong. It should be reversed. Well, the integral from 4 to 1 is the opposite of the integral from 1 to 4. And what was the regular integral from 1 to 4? -2. So the opposite of -2 is +2. Those are pretty easy if you know the rules. All right, next. -1 to 4. So, I kind of went fast. Go ahead and write down these. If you write down this, we're going to use it for 3 slides. Okay? So go ahead and write down the example.
I'm not listening to Pop Smoke. It's Winnie Games is short.
They don't look that weird in real life. Usually.
I've got to go to distracted. I got mounted. It was so worth it though, because I was watching it. It was so worth it, baby.
Christmas. Huh? Wasn't it?
It is the picture. Yeah. The David is the just that.
All right, next one. Ooh. Let's do -1 to 4. I don't see a -1 to 4 up there, do you? But -1 to 1 has a net area of, I don't know whether the function is positive, negative, or what, but it must be mostly net. -1 to 1, -1 to 1. It must be mostly positive if the net area is 5. Do you agree? 5. Okay. And then 1 to 4. 1 to 4 is -2. So this area from here to here was 5. This area from here to here is -2. These are adjoining intervals. They're adjoining intervals where one leaves off, the next one picks up. So we have a rule for this. What do you think the total area is going to be from -1 to 4 if we had an area of 5 from here to here and then -2 from here to here? 3. So there's a property, and when you write it down, it's called, I believe this one's called additivity. Additivity. Yeah, notice the one between sum and difference. Sum and difference, you're actually adding 2 different functions together. Additivity, you are going from A to B and then from B to C. You're adjoining intervals, A to B, B to C. You add up those integrals. And the next one. Find the integral from -2 to 2 of h of x. Well, there's only one up there with h of x. It goes from -1 to 1. What do you think? -1 to 1. The net area is 7. How about -2 to 2? I have no idea because I don't know what. It's not necessarily symmetric, right? Not possible. Does it make sense? Can't do it. You don't know enough information to be able to do that. All right. So please copy down those properties and a couple practice problems using those properties. One, two, three. 7. Ignore 7. 11, 14, 18. Did I say ignore 7?
That's okay.
Doesn't even have stuff on
Hey, easy as 1, 2, 3. Go for it. And copy the properties.
already out.
Have a wonderful day.
Have a nice weekend. Everybody's making us.